Hello. In this lab, we will talk about Faraday's law. Our objectives in this lab is to collect observational data of a magnetic field that goes into a tube of aluminum foil, and we model this interaction between the magnet and the aluminum foil computationally, and compare those two results. Our main results in this lab is to find the time for the magnets to fall into the tube and get out of it. Our physics principle that we use in this lab is first Faraday's law and Newton's second and third law, and finally Biot-Savart law. Measurements of this lab, we first measured the length of the tube, including the width and radius. We used the mu value of our third lab for the magnet and the mass of the magnet also. For the trails, we used 5 trails to get the average between them to be 1.31 seconds. For the code, we first initialized the code by plugging the numbers of our real-life observation from the tube and the magnet. Second, we did the calculations. First, we defined the function of the dipole or the magnetic field of the dipole from our previous lab and plugged it. And then we got the flux, which is we got the d flux over dt, which is equal to the EMF that we use to get the induced current value. And we finally calculated the magnetic force on each ring, and we integrated those rings together to get the final value of the magnetic force on the tube. So this is our computation method. You can find on the left the tube. Inside of it, between the red and blue colors, is the magnets in which it falls, but that's just a picture of the falling. And in the right, you could find the graph of the velocity versus time. You could find at the beginning the velocity first was decreasing until it increased a bit, and then stayed, which we have like zero acceleration between those time between 0.2 seconds and 1 second. And finally, when it got out of the tube, it starts decreasing again. To interpret the stimulation, our first question is that density of the coloring, which means which color corresponds to clockwise or which one corresponds to the counterclockwise. I believe is red for counterclockwise and blue for clockwise, as if we do the right hand rule, we could find that. And the second question, what happened to the dynamic of the system when you flip the magnets around? Basically nothing would change. And how's the total time in tube compared to the computational system? In the real life, time would be higher than in model because of the air friction and also the friction with the tube. Final question is, what does the shape of the velocity versus time plot tell us about the forces acting on the pair? As you said before, the velocity here, we can find that the acceleration at the beginning was negative, or the forces were negative at the beginning, and then it increases to be positive, and then to the zero, which is the acceleration, we find it to be equal to zero, and then to the negative. And finally, what if the resistivity of the conductor reduces as we close to zero? According to the Ohm law, the time will be much larger because the volts or the EMF will be much larger. And what if there are holes and slots were cut into the tube? How would that affect the ring currents in the model? That would reduce the time for the magnetic to fall, because the rings that we use in the computational method would be decreased, and so the current will be higher. I mean lower, so the time would be decreased or reduced. Thank you.